One view I have of this is, how could we have 100 million teachers and one student, which is like, or a handful of students that are, quite capable models being taught new things by people all the time, and then everyone benefiting from that teaching that people have done.
Yeah, I actually would like to think that's the world we're headed into. Thanks for doing this with me, Jeff.
I'm delighted to be here. Thanks for having me.
I'm going to start by embarrassing you. I want to hear about what it was like to be Jeff as a kid, because even the people who I think are engineering superheroes look up to you as an engineering superhero. I think it all kind of concentrates. There are very few people I know who have more of the sort of arrows pointing up of admiration towards a single engineer than you. What was it like when you were a kid? Like, did you make stuff? Did you start being an engineer later in life? Like, what was it like when you were 5, when you were 10?
Yeah, I guess, thank you for the kind words first. I think I had a bit of an unusual childhood in that we moved around a lot. So I went to 11 schools in 12 years. At a very early age, I liked building things with Legos. So we always had my Lego set in the moving van showing up in the next place. That was always fun. When I was about 9, living in Hawaii, my dad was a medical doctor, but was always interested in how sort of computers could be used to improve public health. And he's, at that time, the way you got access to a computer was you went and preached to the mainframe gods in the basement of the health department or something, and they implemented whatever it is you wanted. And the turnaround time was not great. So he saw an ad in the back of a magazine for a kit computer that you could solder together. This was an IMSI 8080.
Like a Sinclair?
Like an IMSI 8080, pre-Sinclair. So right. I'm dating myself here. It was like one of the first, probably about a year and a half before the Apple II came out. Uh-huh. And it was like basically initially a box with blinky lights and front panel toggle switches. Eventually we got a keyboard, which was good because you could enter like more than a single bit at a time. And then we got a basic interpreter for that. So I got a printed book at that time. There's no like open source software you download, of 101 basic language computer games. And you could like type them in and then you could play them and you could start modifying them. And so that was kind of really how I got introduced to programming. I sort of liked the idea that you can have something and then use it and play with it, and that software could be used by other people. And then we moved to Minnesota, which was like a really amazing progressive state. So they had an entire computer system for all the high schools and middle schools in the state that everyone could connect up to. And there was like online chat rooms with other people across the state you never met, and, interactive adventure
you were like
games.
13, 14
I was like
at the
13,
time?
14 at the time. So this was like the internet before the internet, maybe 15 or 20 years before that kind of interaction with other people in a virtual setting became commonplace. And so I sort of spent a fair bit of time interacting with other people, learning, how to write software that was multi-user, from example software that other people had posted. And that was kind of fun. I'm terribly undexterous, so I'm very, very bad at building physical things, but software is nice because Do
you remember what the first non-trivial thing you coded was?
Coded myself. Well, when I was 13, or 14 maybe, one of the soft multi-user games that I played in this online system, the PhD student who had written it was graduating. He decided he would just publish all the source code. So I got an illicit access to a laser printer and printed like the 400 pages of source code and said, I'm going to make this Pascal software written for this multi-user mainframe thing work on my like UCSD Pascal system, a like individual box at home with a couple of terminals plugged into it. So I had to learn a lot about how to do like multi-user, multi-port interrupts, and, you have multiple terminals giving you input. How do you sort of schedule all that? The Pascal dialects were not exactly the same. So I had to figure out how to make that work. And so that was a lot of fun. I learned a lot about, concurrency and things like that, kind of muddling my way through, not with any principled discovery of it.
Obviously, you can and do write in dozens of languages. Mm-hmm. Is there a particular language? Like, I haven't been a serious coder in a long time, but I still think in C. Mm-hmm. That's where I did my most serious coding, and I just sort of like never got out of it, even though languages moved on from C. Like, how about you? Like, is there a language you think in?
I probably use C++ the most by far, just because it's a very low level performance oriented thing. And a lot of what I do is distributed systems work, that sort of encourages that kind of low level language. But I have kind of a love-hate relationship with it. It's completely unsafe. Like, you can overwrite memory, and more modern languages have a lot of nice attributes to them. So actually for my thesis, my advisor in grad school was both a compiler and a programming languages. Those were his two areas of expertise. So what do programming languages people do? They invent programming languages. So he invented a language called Cecil, which had a lot of really nice qualities in terms of the kind of object-oriented methodology. You have like very nice ways of sort of making modules that are sort of good for large-scale software systems. So we wrote an entire compiler for 4 different languages in Cecil. It was like 100,000 lines of Cecil. The back end of it turned it into like 30 million lines of C code. And then we had a assembly backend as well. So that was a lot of fun. And like the expressiveness of that language and the standard library design for it was actually quite nice. But it's like probably been used by 50 people in the world, sadly.
Understood. Do you remember the first time kind of artificial intelligence like captured your imagination? Like, I remember for me seeing genetic programming, this is probably 91, maybe 1990, seeing genetic programming using Lisp code and being able to do sort of sexual crossover between chunks of code.
Like cross these two S expressions and who knows what you'll get.
But that was the first time where like artificial intelligence moved from, it's not that I understood it or that I was particularly good at it, but it moved from like a word that was in my peripheral vision to like, ooh, like it just felt kind of more real and intense than it had before. Was there something like that for you where?
Yeah. So the first real exposure I had was as a senior at University of Minnesota. I took a 2-quarter sequence on distributed and parallel programming. And as part of that, we got introduced to neural networks because they're a very highly parallel form of computation. At that time, there was a lot of excitement about neural networks because they seemed to be able to solve kind of interesting small-scale problems that couldn't be solved with other methods.
This is also the early 90s.
This is 1990.
Yeah, there you go.
So like late 80s and early 90s, there was some excitement about neural networks because they seem to be like a good abstraction. They're sort of loosely based on kind of how we think real sort of brains in people and animals work, where you have this kind of this artificial neuron abstraction that gets some inputs from below. It sort of decides, is that interesting? And then it decides to either fire or not, and what strength to fire with. And then you build more interesting systems out of lots and lots of those neurons, and also many, many deeper layers of those. So at the time in 1990, a 3-layer deep neural network was deep. Now we're doing like 100-layer neural networks. But that was my first real exposure, and they seemed to be able to solve kind of artificial pattern matching tasks that other approaches couldn't solve, because you could build these, multi-layer abstractions and the right sort of features would emerge automatically. And so I decided the professor in the class was an awesome faculty member, Vipin Kumar, and I asked him, can I do a senior honors thesis with you on parallel neural networks? Because I thought like, oh, maybe we can train bigger networks with like using the 32 processor machine in the department instead of 1 processor. And I said, oh, that's going to be great. We're going to make amazing neural networks. Turned out we needed like 1 million times as much compute power, not 32 times. And so I sort of implemented actually two different methods of parallelizing neural network training. There was one where you would take the input and then you partition it into sort of different batches, and each processor would have a copy of the network, but it would only see part of the data. And then the other approach was you take the bigger network and you chop that into pieces, and you send all the patterns through all the pieces of the network. And then, so that today would be called data parallelism and model parallelism, but I didn't know what to call them. So I called them like pattern parallelism and something else in my thesis. But that was sort of my first exposure to neural networks, and they always felt like the right abstraction. But
neural networks.
Yeah, neural networks.
Well, I'm really curious. I will out myself because I did get sucked pretty deep into evolutionary computation, and neural networks generally were completely out of vogue by the end of the 90s.
Absolutely.
In artificial intelligence.
Yes.
So I will say I had lost faith in them. Yeah. I didn't get it, at least circa, 2000. Mm-hmm. Did you ever lose the faith? Was there some period in the middle where you're like, yeah, that's probably not it just because the field had given up on it? Or you kind of kept the faith?
I kept the faith, but I put it on the back burner, and I tend to meander around a lot of different areas. So I kind of then said, okay, I'm going to go work on, public health software for WHO for a year before I go to grad school. So I did that, building sort of HIV/AIDS prediction models. Then I went to grad school intending to study parallel programming because I really liked the thesis I'd done and that sort of introduction to it. Switched to doing compilers with my advisor because that seemed super interesting, and I always liked kind of performance-oriented things. And then when I graduated, I wanted to be somewhere where there were lots of things going on. So I went to a research lab in downtown Palo Alto for Digital Equipment Corporation because they had 35 people in 20 projects doing all kinds of different things. Like the first multi-core processors were developed there, but there were also like weird handheld devices before phones and things like that were a thing. And some interesting work on profiling tools and user interfaces. I just like being in a place where there's lots of stimulating ideas and conversations and people who know things you don't.
It's been talked about enough. I'm going to skip over how you got to Google because I think that you've talked about that a good bit. But because I think it's going to be relevant when we talk about Google Brain, one of the really inspirational things that you've done, you were the first engineer at Google, right?
No. One of a handful.
One of a handful. And you have made a career out of kind of starting over, like getting really big things going, handing it off, and then backing all the way to being an IC again, and then sort of doing it again. And you've done this quite a few times. And I think one of the things people may not appreciate is the level that you have inspired other really great engineers, that how many people you manage is not the right measure of how much value you're adding. And one of the reasons I think they look up to you is because you've set the standard of not holding on to empires, but like making sure that the thing is like rolling down the hill so fast, so strongly that it's not going to stop. And then you can go find the next snowball to get rolling. Or at least that's how it looks from a distance.
I mean, I think I do like to kind of think about what area would I like to work in next, and what would be a good 5-year-ish journey in some area to, learn about that area, to work with people who know different things than I do. And I've done that a bit in like information retrieval systems, which I didn't have much background in. So helping build some of the early search algorithms and obviously the infrastructure for it. And then working in large scale storage systems like Bigtable and Spanner, a bit in, machine learning for healthcare. And then also kind of the early days of the Brain project where, that started because I was sort of, I had been working on the Spanner large scale storage system, which has a bunch of nice kind of consistency properties. It's meant to span the Earth with a single storage system rather than separate ones in different data centers. And it was getting to be sort of heavily used and sort of reasonably stable. So I was trying to figure out what I was going to work on next. And I happened to bump into Andrew Ng, who I think you had brought in, or Sebastian had brought in to Google X. I bumped into him in a micro kitchen. He's a Stanford faculty member. And so he was here one day a week, I think. And I said, "Oh, what are you up to here?" And he's like, "Oh, I don't know yet. But my students at Stanford are starting to get interesting results on neural networks with, speech and vision-y kind of applications." I'm like, "Oh, really? I like neural networks. We should train really big ones." And so that was kind of the genesis of the Google Brain team was, hey, let's see if we can really scale up neural networks. Now that Andrew and his students had started to see, and others had started to see good results on using GPUs, Moore's law had advanced in 20 years and given us way more compute. Google had a lot of computers in our data centers. So I said, well, let's just do a distributed neural network training system that we can train very, very large networks. So we trained, on 2,000 computers, 16,000 cores using CPUs because we didn't actually have GPUs in our data centers at the time. And said, let's see what we can train. And gradually more and more people started working on the project. We trained, large unsupervised models for vision. We trained a bunch of supervised models for speech, did a bunch of stuff with collaborating with, search and ads and various other parts of Google. Eventually, we had hundreds and hundreds of teams using neural networks based on the kind of like early framework that we sort of started putting together with just a handful of people.
Yeah. So when Andrew was in that chair talking to me about it, his description was almost exactly what you said, except with a much higher degree of needing you. So his description was, I had this secret data, which wasn't at all secret. It's just no one would believe me, that the size of the neural net mattered, that if you just kept making it bigger, it just kept getting better.
Yeah.
That we knew from my students at Stanford. The thing we didn't have was Jeff. What we needed to do was make this attractive enough to Jeff that 1 + 1 could equal 100,000 here, because I think they understood that this was going to take a sort of spanner and MapReduce kind of mentality, the ability to do this at such a scale that it wasn't going to fit on a single computer, the kind of thing that they don't teach you in academia how to do.
Yes.
So one of the things which I think in the early days we thought was going to be important, but maybe mattered a bit less, was the MapReduce part of it, the break up the problem part. Did that turn out to be really critical or less critical than you thought? As you started getting into training these huge networks?
Yeah, it turned out to be quite important. I think we in the early days of the Brain team, we again saw those results where you scale up the model, you scale up the amount of data you train on, the amount of compute you put into training, and the results just get better. So we had a saying, bigger model, more data. And, these days that's been sort of more quantifiably established with things that are called scaling laws, where people have observed, if you double the amount of compute, then you get better results by a certain amount. And it's got this really nice log linear relationship. Log linear is not as amazing as linear, but still, if you make your model bigger and train it on more data, you generally see better results. And so that's why there's this wave of excitement happening now that is really kind of the continuation of that scaling trend. But what we built in the earliest days of the Brain team was a framework that would let us do both model parallelism, where you take a large model and you break it down so that pieces of it are on different computers. And at that time, our networks were not super speedy because it was basically data center and Ethernet connecting the machines. But to get a very large model training effectively, you wanted to parallelize it across multiple machines. And we actually would have different model architectures that tried to have relatively small amounts of bandwidth going between different pieces of the model. So you might put different neural network layers on different machines, and then not have to send all the state for a particular layer to all the machines.
How much did you think about the topology in the early days? I mean, you were all of a sudden trying to do something that was hundreds, tens of thousands after a year or two times bigger than anyone had ever built a neural network before.
Yeah.
Did you just like literally multiply, the width and the depth by 100? I mean, I know you didn't, but like unpack a little bit how you thought about what it meant to make something 10,000 times bigger.
Yeah. So I guess we made a neural network that was 100 times bigger in terms of number of parameters, and the amount of compute put into it was probably way more than that for what anyone had trained at that time. This was like 2011, early 2012. It was like a 2 billion parameter convolution, non-convolutional, but localized receptive field computer vision model. And so the way we did this was we essentially chopped the model in the X and Y dimensions, looking down the model. So the layers would mostly be on one machine as you went up in the layers for receptive fields that were small, looking at the bottom right corner of the image. And then another machine would be looking at the bottom left corner of the image, and go up the layers of the stack. I think it was like 9 layers deep. But you still need to send some information across from the bottom right one to the one to the left of that. And so it was like a 13 by 13 grid of machines for each copy of the model. And then we would train on batches of data, and each copy of the model will get to see a random sampling of some of the data. But then we would synchronize all the parameters by having many copies of the 169 machine setup that would all coordinate through what we called a parameter server. So they were getting, the parameter server had all the 2 billion parameter, pieces, floating point numbers that are adjusted by the machine learning training process, like making.
So that would help them to converge.
Yeah, it would help them to converge. And by parallelizing that across 10 or 20 replicas of the 169 machines, then you would actually get pretty good throughput, and you could train on, tens and tens of millions of images in order to get the model to converge. Because the more training you put in, the longer, the better the results are generally.
From the outsider's perspective, the picture of the cat that ended up on the New York Times, which is kind of like the coming out for Google Brain, is what people remember as like the aha moment. And it's maybe worth talking about. But I bet you had an aha moment before the picture of the cat, where you were like, this is not just a nice to have. This is like a phase transition.
Yeah, there were a couple, I guess. So the cat was really cool because we were using an unsupervised algorithm. And so essentially we took 10 million random frames from random YouTube videos, and we trained the model to have kind of higher and higher levels of features that describe the raw pixels that are going in at the beginning.
Was essentially trying to find a compression algorithm of sorts for random photos from YouTube.
Yes,
kind of.
Exactly. Right. And so the highest level features there, you then kind of use those as the seed to try to regenerate the input data using only the highest level features.
And shocker, it looks like a cat.
Right. There's a lot of cats on YouTube. So the interesting thing was we could look around. I think there were like 40,000 total neurons in the highest layer features. So many different neurons at different positions, at each position, and then many positional neurons. And you could look at what caused those neurons to fire. So you could feed in random images and see what neurons got excited when you fed in, say, images of people versus not, random images. And which ones got excited when you fed in cats versus not cats. And the interesting thing is that the model had essentially invented the concept of a cat through this unsupervised learning algorithm, because it made sense in the optimization algorithm, to devote some amount of capacity to features that are sort of highly correlated with there being a catness in the lowest level pixels of the image. We had other features that were maybe less exciting, but were like the back of a pedestrian or kind of creepy human face. If you average the thing that gets these particular neuron really excited, you can create these kind of like, this would be the most attractive input pattern to make this neuron fire most strongly. And that's what created this cat image, or a different neuron had a like kind of creepy sunken-eyed face person.
Kind of like if you went into someone's brain and you happened to be able to tickle their grandma neuron, right, and then they like start thinking of their grandma.
Right. And then like what grandma images could you feed in that would cause it to fire the most strongly? And you get like a nice average grandma.
Right.
So we called it average cat.
I remember the rate at which the brain team was climbing up the rankings on speech to text and on general image recognition, sort of the ImageNet, which is a well understood, international kind of competition, not really a benchmark that everyone kind of accepted. I remember the rate at which the brain team was climbing up that was just stratospheric on both of those.
Yeah. So one of the things we did with that unsupervised model was we then did a little bit of supervised fine tuning on the ImageNet data set. And we used the ImageNet 20,000 category benchmark, which had more training images in it.
So this is like, these are cats, these are flowers, these are birds, whether it's labeled.
Yeah, except it's 20,000 categories. Right, so it's like, these are German Shepherds. Right. These are like obscure dahlias or whatever. So most people at that time were focused on the 1,000 category data set. We thought that was not as interesting as the 20,000 one, but most people didn't compete in the 20,000 one. But we got a 60% improvement relative error rate reduction in the 20,000 category one with our giant neural network that was 50 times bigger than previous neural networks. And we also got essentially a 30% word error rate reduction improvement in the speech system using supervised training on a model that we could train in 800 machines for 5 days.
And people had spent their lives making much smaller improvements than that.
Yeah, just to be clear, a 30% relative improvement in word error rate was equivalent to 20 years of speech research advances.
Yeah.
And so we were seeing that level of improvement from essentially switching out the existing kind of non-neural network based model that the speech team was using for the acoustic part of the problem into a neural network that would do the kind of the early acoustic modeling, which was great. And also was kind of the genesis of our customized machine learning hardware.
Yeah, well, I'm glad you brought that up. So in the very earliest days, when we were talking about setting up Brain, one of the arguments was we thought that essentially specialized AI was going to need specialized hardware. And because we were really committed at X to not doing pure software plays. Then the Brain team was working so well just using existing CPUs that there were a bunch of reasons it moved back to Google, and that was the right thing for it. But one of the arguments at the time was, I guess they don't need hardware, so maybe this isn't the place for it to be longer term. But then soon after it moved back to Google, you first did TensorFlow, this sort of externalization so that other people could start thinking about how to set up and train these things. But then also started what became known as the Tensor Processing Unit, a specialized piece of hardware. Yeah. Can you unpack that a little bit for the audience?
Sure. Yeah. I mean, so the Brain team actually was kind of a hybrid straddling part Google and part Google X at the time. Where a few people joined the project from the X side, a few people that I knew joined the project from the Google side. We were sitting in Google X buildings, which was great for the first year. And I think we eventually were starting to see really good results with neural networks that were highly relevant to a lot of Google core teams and products, like things like search and speech and vision. And so it made sense for us to be closer to them organizationally and building wise than the X buildings, which were a bit on the periphery of the campus. But it was a great home for the initial phases of the project before we moved. So that the TPU really came about in 2013 when we were starting to see these incredible results on speech. And I started to do what are sometimes called back of the envelope experiments, where you're like, okay, well, if speech is working better, one of the reasons people don't use speech recognition at the time was it didn't work very well. If you get an error every 5 words, it's not actually saving you that much time to dictate things to your phone and then correct lots of words. But if you're getting an error every 30 or 40 words, which sometimes you could do in a sort of nice environment, I was worried people would start to use speech a lot more than they had. And the model we'd trained was highly accurate, but very computationally expensive. So I did this thought experiment of like, well, what if 100 million people start talking to their phone for 3 minutes a day? And so I had a nice slide working out exactly, if we deploy this on CPUs, which was what we had at the time, here's how much compute we would need. We would need like 1.8 with like 28 zeros after it, floating point operations per day or something. And I said, there's got to be a better way. And we know that neural networks have 2 really nice properties. So one is they're mostly compositions of a handful of linear algebra operations. So multiplying matrices or multiplying vectors together, or vector dot product kind of things. And then they're also very tolerant of reduced precision. So unlike, say, high performance computing style numeric simulation software, where you need 64 bits or 32 bits for your floating point numbers, you actually can use, very, very reduced precision. So the initial TPU was designed for inference, and actually only had 8-bit integer operations. It didn't have any floating point at all in it. And then later TPUs, we added this reduced precision format for floating point called bfloat16. So it turns out IEEE had a 16-bit format that turned out to be not very good for machine learning because it lost both some mantissa bits, but also some exponent bits. And for a neural network, what you care about is actually being able to represent a really wide range of values, and you don't care that much about like the 5th decimal place. And so it turned out to be better to lose all the 16 bits from the 32-bit format in the mantissa and keep all the exponent bits.
Talk for a little bit. One of the other huge breakthroughs that happened shortly after that was on the brain team was attention.
Yeah.
I mean, that arguably, from the popular understanding of artificial intelligence and machine learning, more than anything else, the thing that caused that explosion was, you were describing before, like this part of the network was working on that pixel from the image, and this other part of the network was working on that pixel in the image. And the crosstalk was really poor between them because it was just sort of an n-squared problem.
Right. Yeah, I mean, maybe I can rewind one step from the attention model, which was the first kind of, there were 3 breakthroughs, I think. One is in terms of understanding language. So one was this notion that you can have a distributed representation of words or phrases. So instead of representing a word like New York City as, the characters New York City, you instead can have a vector that represents, in a high dimensional space, the kind of inherent meaning and context in which New York City tends to appear. So you might have a 1,000-dimensional vector that represents that, and another 1,000-dimensional vector that represents tomato. That was enabled by a very simple algorithm called word2vec, where you could essentially train these vectors based on trying to predict what are the nearby words that when I see tomato, can I predict the 2 words before this and the 2 words after that from the vector representation.
This would allow you to do something like king minus man plus woman equals queen. That if you have those kind of vectors, then all of a sudden that kind of algebra starts to work.
Yeah, it's kind of amazing, actually. In very high dimensional spaces, there's lots of space in the 1,000 dimensions to put lots of different meanings of words, but directions also start to become meaningful. And so going in this direction in this 1,000-dimensional space tends to be the way in which you get from the masculine form of a word to the feminine form of a word. So the way you get from bull to cow is the same direction as going from king to queen, is the same direction from he to she. And different directions mean different things. So this is the way you go to get the present tense to the past tense of a verb, no matter what the verb. So that was pretty eye-opening. The next thing that happened was three of my colleagues, Oriol Vignals, Ilya Sutskever, and Kwok Lee, developed a model called sequence to sequence, which used LSTMs. So an LSTM is sort of like a thing that has a vector as state, and then it processes a bunch of words or tokens, and every time it updates its state a little bit. So it can kind of scan along a sequence and remember in a vector-based representation all the things that it's seen.
It's the short-term memory on a running basis for the system.
Yeah, exactly.
Yes.
And so you can like absorb a sentence and end up with a vector that is the model reading and understanding that's, or, making sense of that sentence in this high dimensional space. And what turned out to be interesting is they developed a version of this called sequence to sequence, where you could have one sequence and read that input sequence and then use that to initialize the decoding of a sequence you're trying to produce. And so it turns out this is a really good way of modeling machine translation. So you can take in an English sentence and then from the vector of the English sentence, produce the French sentence one word at a time. But it also turned out to have applications in sort of medical records, in language understanding for a single language. Turns out you can map all kinds of genomic sequences onto these kinds of sequential models. And then the attention mechanism that was developed in the transformer work by Noam Shazir, many 7 or 8 other co-authors, was really this idea that instead of trying to update a single vector at every word that we see, let's just remember all the vectors. So we have all the intermediate vectors of all the states we've gone through, and then let's just pay attention to all of them. And so attention is all you need. It's the name of this quite seminal paper where they developed this transformer-based attention mechanism that sadly is n squared in the length of the sequence, but produces amazing results.
It's tough from a space perspective, but it makes the computation much more tractable.
Well, I mean, it has a few nice properties from a computation standpoint. So one is when you're processing a bunch of text, you can actually process it all in parallel. So unlike the LSTM where you have this bottleneck sequential step of you see a word, you need to update your state and get the new state before you can then go on to the next word. Instead, here you can take your 1,000 words and process them in parallel and compute all the different state you need to look at and then attend to it. And so that turns out to be a much better fit for modern, ML processors that have very high degrees of parallelism in their matrix units.
So most people listening to this are operating a much more philosophical level, right? They go to Gemini and they ask a question and they can have a dialogue with it that is a little bit mind-blowing for them.
Yeah.
At the sort of much more philosophical level, where do you think the world is going? Like, not just like what products will Google have next year, but like philosophically, how do you think all of this is going to play out over time, and how will the citizens of the world experience this?
Yeah, I mean, it's pretty remarkable the improvements that have been happening in the models over the last, say, 6 years. I think that is testament to larger scale training setups that can train bigger models, more data. So that's one aspect. The transformer model architecture enables these models to be more powerful from a model architecture perspective. Curation of data makes the models higher quality. If you train on high quality data, you generally get a better one than if you train on random data. And then the models have gone from kind of texty models to fully multimodal ones that can deal with all the different human modalities you can imagine on both the input and the output side. They can deal with you talking to the model in speech, or giving it a video and saying what's in the video. And now they're starting to be able to, can you generate me a video that has like a unicorn jumping over a school bus and my dog in the front, and you give it an image of your dog. So I think these are kind of pretty interesting capabilities. The ability to transform one modality into another. You see this with the like new Google products like Notebook LM. You can put in a whole bunch of PDFs and say, please generate me a podcast with 2 AI generated voices rapping about the exciting, quarterly report I put in for this company or whatever. And I think that's pretty interesting. Being able to, I think these models behind the scenes can actually like do a lot of work that they're starting to do now on behalf of what a very high level request is.
I agree. I think we're going to see a huge shift from humans making things to humans doing much more work on the specifying of what they want.
Yeah.
Which won't necessarily be easier, but I think it'll be more fun and it will unlock a lot of creativity for people to have to be super specific. It's sort of like going to a relatively dumb genie that can make you almost anything. But if you can't be specific about what you want, you can't expect something particularly special to come back the other side. And I think what is currently known as prompt engineering is going to turn into how we all work.
Yeah. I think you can actually give these very powerful models very high level descriptions of what you want. Can you prepare me a report that summarizes the trends in wind and solar power and the price trends over the last 20 years, and also how much deployment is happening in South America, right? And you could say that, and the model will actually probably do a pretty decent job at that through some retrieval, some reasoning about things it already knows about solar and wind and what those concepts actually mean. And then going off and iterating and getting more data when it sees that it needs some information there. And that would have taken a human a huge amount of time. There's no single like document in the world that exists that has that. So it's able to combine together information from multiple places, cite it appropriately sometimes when that makes sense. You can do the same thing with videos. We mentioned the unicorn and the school bus. It's a delightful interaction style.
I'll give you an example that I do, and I'd love to hear something that's not code, because I'm sure you do a lot of code with Gemini. But like one of the things I really like to do, I think in terms of like the pros and cons. And so I love asking Gemini, just give me 10 arguments for something. And then give me 10 arguments against that same thing.
Yep.
And it's remarkably good and fair at both, because it doesn't have an axe to grind on either front. It just dutifully comes up with a lot of surface area so that I don't have to come up with those things. I can start mushing them against each other and decide which I believe.
Yeah, I like to think of it as like a Socratic partner for you.
Yeah, exactly. What's something that you do, not code, that you find useful?
I will use it to like just explore a new area. I'm like, can you tell me like exciting new trends in some new area that I'm not that familiar with? And it will go off and, give me some information that I can then use to ask follow-up questions. I'm like, okay, can you tell me more about this? Or, what are the trends in this particular area that are, really developing in the last few years? And it's quite good at that. And quite useful. I think combining this kind of general world knowledge with your own personal state is going to be a really important trend. Like, can you help me find restaurants that, I might like in Arizona next week, that are similar to the ones I went to in Tokyo, right? Last year. And like, it should know what you did, with your permission, of course, and be able to sort of offer suggestions that are tailored to a very personalized sort of view of what it is you might like and what you've liked in the past.
Speaking of permission, obviously Google cares very much, but I know it's also very personal to you. The issues of sort of safety, security, and responsibility around artificial intelligence. What are some of the things that either you're worried about or that you're excited about that are sort of causing Google itself, but the world more generally to sort of be on the right trend, or you think things that we need to hew in one particular direction or another to sort of stay on the right side of the security, privacy, copyright, other legal issues. What are some of your thoughts there?
I mean, these are really good questions to be always thinking about. Is, how should we as technologists think about our technology being applied in different spaces? How should we as society, this is clearly a technology that's going to affect many, many things. It can affect education and healthcare and, basically every sector of what people do in the economy, creation of new kinds of things, are all going to be sort of impacted by what is possible now and what will be possible, say, 5 years from now and 10 years from now. So I think it's really good to think about how can we as society shape this so that we get all the positive outcomes, or as many of the positive outcomes of AI as we can. Like, one that I'm particularly excited about, or a few, are it could dramatically help in education, particularly in areas where there isn't much access to sort of, maybe student-teacher ratios are very large, but you could have an individualized tutor for every student that could help them learn anything they're interested in. I think that would be incredibly transformative. In healthcare, I think the ability to connect, obscure trends that are maybe not very visible to an individual doctor, but are, incredibly apparent when you train a model to have the experience of many, many doctors, that would be, very transformative. There's all kinds of interesting privacy issues related to healthcare, but I think if we get that right as society, we will actually dramatically improve outcomes. At the same time, there's all kinds of use cases for this technology that are quite negative, like being able to create misinformation more readily. It's not a new problem, but all of a sudden you can make realistic sounding voices with realistic looking videos of someone saying something that they didn't actually say. And that, can spread on social media, can, affect people's lives and what people believe about the world. So I actually was a co-author on a paper with, I think, 9 authors, great group of people, called Shaping AI, which is sort of how we should think about many of the issues in AI development, and how kind of there's a bunch of interesting kind of societal questions and how we want to steer and shape it to make sure that we get some of the outcomes that we want for impactful areas like education and healthcare, and also how we can sort of think about technologies or policies that may sort of minimize some of the downside around misinformation or other kinds of things. So.
Yeah, I'm glad to hear that. One of the things that gives me some comfort is, I remember in the early days of YouTube, I'm sure you do too, there were a lot of people putting songs into their videos that wasn't their song,
right,
and then getting and monetizing those videos. And that was making the original maker of the song really grumpy, understandably.
Yep.
But YouTube got ahead of that to the point where then the person who had made the song, or the company that owns the rights to that song, could either cause that video to not be there, to not get to be monetized at all, or they could get cut in on it.
Right.
And so what started as a bit of a feeling of Wild West, YouTube actually got to a place where I think the creators all ended up feeling like they were better together, and YouTube had actually sort of helped bring balance to the force in that particular space. And so I'm hopeful that some of the companies like Google, by leaning in, by listening to what people are concerned about, can, in similar creative ways, sort of give back control to the people whose data it is in the right ways, so that we can all be better together. I don't think that that's not possible. I just think it's going to take creativity.
Yeah, I think there's a interesting direction that we should collectively as society pursue, which is how can we get, data that is, being trained, that machine learning models are being trained on, how can we sort of effectively make sure that the value that that data brings to these models is effectively compensated or, we already allow people to opt out of us training on their data. But a better thing, I think, would be to enable people to give data that the model should be trained on and get that, organizations compensate people in proportion to the value that data brings. And there's interesting technical questions of like, okay, if you give data, but there's already lots of other data that says the same thing, that has proportionally less value than something that is sort of novel and truthful and high quality.
Yeah, it's a really interesting question. If I'm the first person to teach the robot what a banana is, I mean, other people can do it. Should I? It's not even, there's no right answer to whether I should get more credit than the person who does it second.
I can see why that would be appealing.
Oh my goodness, that was quite a pun. One
view I have of this is, how could we have 100 million teachers and one student, which is like, or a handful of students that are, quite capable models being taught new things by people all the time, and then everyone benefiting from that teaching that people have done.
Yeah, I actually would like to think that's the world we're headed into.
It's like a flipped classroom.
Yeah. One of the weird things, and again, I know that you're really close to this, is as we're trying to make these models more powerful so they can help humanity more, and we're trying to sort of stay ahead of like security issues, privacy issues, et cetera, we want to understand these models and why they're doing what they're doing.
Yeah.
But these models are now so big that we've mostly left behind understanding these models in the way that you or I used to understand a piece of code.
Yeah.
And we are now understanding their understanding in something that's feeling more and more like neuroscience, where we're looking at parts of these digital brains and trying to sort of back out explanations for why they do what they do. Like, where do you think that part of the field is going, of sort of understanding their understanding?
Yeah, I mean, some of the people doing work in this area call this interpretability. Can you understand what the model is doing and why it's doing it? And for this particular input, why does it behave in this way? To your point, I think it is a little bit like neuroscience. One of the advantages that we have, though, as a digital artifact is we can probe and measure anything we want very easily, as opposed to like real human brains who get a little upset if you try to put a probe on that particular neuron at all times. So that kind of helps us with better understanding. And I kind of think, a lot of times people are trying to do beautiful visualizations of what's happening in layer 17 of a 70 layer model for this particular input. And that's useful, but that's a bit of a static view. I think one direction interpretability might want to go is, if I want to understand why you made a decision, I would just have a conversation with you. I would say, okay, so why'd you get the green car? That seems like an odd choice. And then you would reply, and then I might ask a follow-up question.
And it might be a bit of a post hoc justification for my behaviors. Just because I say that's why I did it doesn't even necessarily mean even that I believe that that's why I did it, or even if I believe it, that that's truly what my motivations at the time were.
It's true. But I do think like the interactivity of probing the model and why it behaved in a certain way might be a sort of more interesting direction to, because when you're debugging software, you want to print some values and you're like, well, those ones don't make sense. How are they computed? So you want to then go back to like earlier values that influence the computation of this value. So I sort of think of this as like, okay, you ask a high level thing. Can you explain this very high level decision? And then you're like, well, that doesn't make any sense. Like, why did you believe that? And then it can it can sort of
unpack
it and give you, the ability to interrogate it or ask it questions depending on how you feel at the moment.
I'm not a fan of going down the AGI rabbit hole, so let's not do that.
Okay.
But without using that term, at some point, computers will probably be making their own breakthroughs faster than we're making them.
Yeah. It's true in some subfields now, I think.
Yes. But, well-informed people still disagree quite a bit about whether we need 0 more big breakthroughs, 1 or 2 more, we actually need 5 more big breakthroughs. What's your kind of gut on the number of kind of The sorts of things you talked about over the course of Brain, being some of those kind of breakthroughs. Do you think we need a few more of those, or we just need in a couple more years and a couple more factors of 10 of compute?
I think the reason I tend to steer away from AGI conversations is lots of people have very different definitions of it, and the difficulty of the problem varies by like factors of a trillion.
Yeah.
Right? Like being better than the average person at most tasks, that, models today, at least for non-physical tasks, they're probably already at that level because most people are not that good at a random task that they've never done before. And, some of the models we have today are actually pretty reasonable at most things. They will fail at a lot of things. They're not human expert level in some things. So that's a very different definition than being better than the world expert at every single task.
Well, that's why I was choosing the question of how many breakthroughs away are we from the system being able to make its own breakthroughs faster than we can make it for them.
Yeah, I think in certain domains, we're not that far away from that. And we're actually probably already, close to that in some domains. And I think we're going to broaden out that set of domains. It's going to have to be an area that is amenable to a fully automated loop of, generating some ideas, trying them out, getting some feedback about whether that idea made sense, exploring essentially a very large space of, possible solutions to some problem. And when you have that characteristic, we've already seen that reinforcement learning algorithms and large scale search with computation actually are quite effective at this. Where you don't have that characteristic, there's no clear reward signal, or the evaluation of this particular instantiation of an idea actually takes you 2 weeks instead of a minute. Like that kind of thing is going to hamper that being true in every domain, I think. But there'll be a lot of domains where automated search and computation actually can accelerate progress, scientific progress, engineering progress. All these things I think are going to be, important for advancing what we as people can do over the next, 5, 10, 15, 20 years.
You said before that you like to sort of always be looking for what the next 5-year trajectory is for yourself.
Yeah.
What do you think the next 5 years is for you? Like, how do you want to spend your time? You might be wrong, but what's your current guess?
I think I want to spend some time figuring out how we can get incredibly capable models much more cost efficient and able to be deployed to, billions of people. Right now, our most capable models are reasonably expensive in terms of computational cost. And I'd like to make systems that can make that much, much better. And I think I have some ideas percolating that may or may not work out, but that's always the beauty of like trying to go in a direction. Sometimes exactly where you thought you go. Sometimes, you get partway there and you meander off a little bit, but you throw off useful things in the interim while you're trying to get there.
Amen. Jeff, thank you so much for doing this with me.
Yeah, thanks. It's been great. It's a blast being back in the UX building.
Yeah, thanks.